Today we have a speaker, Vlada Limic from Strasbourg University, with the talk Excursion representation for stochastic block models. Please.
Well, thank you very much for the invitation. I prepared this especially for this seminar, and I'm very happy to
Is it my computer?
Do you hear me?
Yes, now we hear you.
Okay. There are things that he said a month ago and wrote about, and I can use them. Okay. So I will remind you of the random graph, the most famous graph in the in the world, random graph Erdős-Rényi, GNP. And okay, let me see if I can, I'll point maybe from time to time. So here, the first parameter n is the number of vertices, p is the probability of connection, and for a specific p, between usually positive and smaller than 1, there are some edges. So every edge appears in the graph independently of others, and either they are open, meaning that they are present, or they're closed, meaning they are not in the graph. And then people noticed very early on that you can get a network, meaning an evolution of random graphs by varying this p. And I think David must have told you about the coupling. Yes, for sure. He told you about the coupling where p can vary from 0 to 1, like in percolation, and the bigger the p, the more edges there are. So it's a really an evolving network with growing clusters. And then there was, by the way, if you have questions at any point, please interrupt, and especially if there is technical problems, I would like to know. So then this is a model from early 60s, very famous Erdős-Rényi paper, must have been cited thousands of times. And then Stepanov in 69, that I learned only recently because I went to some of his papers. He already he did some work on the very interesting work on random graph model, and he Poissonized, one could say, I mean, there is no right expression for this, but let us use Poissonize the model in the sense that he changed the parameter from p to 1 minus e to the minus q. He brought in exponential, independent exponential. And then all this, I think independently in 97 also brought in, I mean, he studied also this model. It turned out that it is more convenient when your p is expressed like this. It is simply more convenient. Now you have a growing network where, okay, let me show it here, where edges now arrive as independent exponential. So exponential rate 1 between every pair of vertices. And then Aldous did more. So in his very well-known paper in 97, he generalized the random graph in the sense that now at every I sits some mass. Before, this mass was 1. Now it's some positive number. And then the connections arrive exponentially, but they arrive at the multiplicative rate. So you have, instead of IID exponential rate 1, just like in the generic Erdős-Rényi graph, here, for example, this edge is closed at exponential rate x4 times x12. And maybe there is actually q. So it's no, sorry. It's right. So it is truly exponential, multiplicative in the rates, and then the probability that the graph GN Q has this edge x4 connected to x12 at time q is 1 minus e to the minus q for the time, e to the minus q, x4, x12. So this is the probability. Okay, and then you could study this evolving network, random network, and then you realize very soon, and I think I mentioned it in one of my talks from 2 years ago or some years ago, in this seminar, that actually connected components are formed because edges connect. And then these connected components, they also have multiplicative rate of merging, because these two components will connect when some, you wait for one edge between either it's this one or this one or this one or this one. You wait for the minimal edge between these vertices and those vertices. And the minimal edge arrives, these are independent exponentials, so it arrives at the rate which is the sum of all the individual rates, and you see that it is the product of the two masses. So we call this, mass. Here is the sum x1 plus x3 plus x2 plus x7 plus x10. And the mass of this one is x4 plus x6 plus x12. And the point of this slide is to remind you, okay, that the mass is conserved, meaning when the two components finally coalesce, there is now the new, bigger connected component, and then the sum, you just sum over all the masses or over the masses of the two components, and that's now the mass of the new connected component. And then what already Aldous did, he did many things for this model and similar, so analogous things, but for this is very good generalization. He ordered the connected components according to their mass. So this is, here I have C1, C2 up to Cn. This is the total size of the well, you could have some arbitrary finite number of vertices, and even you could start from infinite states. But let's not go into that because we are talking today about something else. And you will arrive to some number of connected components. Suppose that initially you have finitely many vertices, then you will have finitely many connected components at any future time q, and you can order these components according to their mass. And then I mentioned already that I gave this talk a couple of years ago. There was a talk that I gave on this model and how one could encode the masses of these connected components. But we will do a simpler version here, the way David did, except in David's talk, all the vertices had mass 1, and the time was specifically C over N. So his walk, I mean, this is something called breadth first walk by many people, including me, or simultaneous breadth first walk, it doesn't matter. So his walk was a bit different. So it was a different expression, but we'll use this one today. And it is a process where you learned already a month ago, I mean, you were reminded. So it is like a Poisson because you have these exponentials here, but actually from every Poisson process, you have n Poisson processes and you let them run. But from everyone, you keep just the first jump, because that first jump is something related to it belongs to the vertex. In some sense, you Poissonize, well, it will be about the edges, but somehow the number of vertices is say n, and for each vertex you have an independent exponential. I did not maybe write this here, but let me write it then. Maybe just even write it. That psi I is exponential rate xi. So in David's talk, there was not a problem. I mean, he didn't, he just said IID exponential because his mass was equal to 1. Every vertex had the same mass, but here they have different masses potentially, and they're independent. Okay, so you run these processes, and this Q. Okay, so Q is the coalescent time, and S is auxiliary time. S is the time of the walk, Q is the time of the coalescent. So that's why right here X is the initial configuration, and we observe the coalescent, meaning this network, evolving random graph network. We observe it at time Q. And so you have this walk. It's kind of, it goes down at unit rate, negative rate. And you keep the first jump of these possible processes, the rest you don't keep. Okay, and so my idea was here to demonstrate you how this goes. Let's see if I can do it in real time. So this is the picture of the process. So first it goes for some time, and then you have the first random variable. These are ordered statistics, and I already ordered these jumps here. Okay, let me just try to. Okay, so I ordered the jumps. I understand. This is not the the no. Okay, never mind. I cannot do it because it's a copy of the original talk. Okay, so what I wanted to do here is, so now there is this first jump, let's say of this size, and then in fact, I mean, it's just, I should be putting a little node, empty node, and now here the full node, and then it goes down again, and there is the second jump, and so I color coded them. Okay, second jump, and then it goes like this. Let me, okay, goes down, and then there is the third jump. Okay, I'm not drawing it perfectly, I'm sorry. Fourth jump. It's something like this, and fifth jump. So the jump is of the same size as the rate. That's the point. Okay. And then the point is that with these, okay, so this is the process Z. Let's say approximation. It's not perfectly drawn, but it is the process Z. And now, how do you construct the graph? It's an encoding of the graph, of the random graph at time Q with these masses. Well, you have to, that's what David did last time. You listen. You kind of, okay, the first jump just tells you from which vertex you will start. So the graph will start growing from pi 1. So that's this pi 1, this thing. It is the vertex whose corresponding psi is the smallest of all the psi. This is the minimal psi 1 over q. Okay, and then for an interval of this length, the same length as the jump, you start listening here for the jumps, or rather you start listening here. That should be here for any neighbors. And the point is, I think I have a slide about, no, I don't have a slide about that. Other random variables are independent exponential. So their residuals are independent exponentials. And so, for example, any psi later on, the probability that psi2 actually falls, psi2 over q falls in this interval of length, it is the length x pi 1, it is the probability that psi2 over q is inside psi1 over q, psi1 over q plus x pi 1. And that's the knowledge, knowing the filtration at psi1 over q. So with this knowledge, it is precisely the probability that the exponential, well, residual exponential, okay, it is on the event that, psi p1 is the smallest. Okay, then some other, not psi2, let's say psi pi 2 or psi, I'm sorry, here I should be writing some other index that is not, so j is different from pi 1, some j. Okay, so you know that this is not the random variable that happened, and you're asking what is the chance that this random variable is now, becomes a child of pi 1. Well, it is truly exponential probability, and let me write it here. It is 1 minus e to the x pi 1, and here I have a q. Q comes from the fact that I'm dividing psi j by q, and psi j has xj as its rate. So this is the rate of xj, and I have q. It is precisely the connection probability in this network. In the generalization. So this is how you arrive to an edge pi 1, pi 2, and then you keep going. So after this, there is an interval of listening for the, listening for something. It is not drawn to the scale it should have been, but okay. You listen for the children of the next vertex in line, and you keep going. And at some point, so let me not go into details because I have so I'm passing on to the next slide, facts which we've just verified or will verify soon, or if we didn't, just trust me. So for each fixed q, zxq encodes a spanning forest of connected components of this graph. So this graph G, I guess I called it here GNQ, but it could be called GXQ. So it is XQ. So it simply goes through the vertices and decides who is connected to whom. Once the vertices are discovered in size biased order, that's because you have exponentials with their rates. The rates are decided, they are exactly those that are, the rate of a vertex appearing, the rate of the exponential, which is linked to the vertex, has rate equal to its mass. And that's the size biased order immediate of the vertices, gives you the size biased order. The connected components correspond to the excursions above past infinity. This is what David explained very well in his simplified case, where every vertex has mass 1 and the time was some specific C over n. The connected components are also discovered in the size biased regime. Well, size biased order. This is something that I talked about, and I will okay, it is something that is not hard to realize, but you have to do some thinking. And in fact, we also wrote up an argument in our paper with David and Vitaly for the stochastic block model, which is a more complicated model, and so you can look it up. But I think everyone here can do it. So passing from the vertices ordered in the size-biased way to the components. And this is interesting, the last bit. It is interesting for today's talk. That actually, when I used to think about, and still on many occasions, I think about the excursions of Z and their lengths. Sometimes it is nicer to think about this time. So these are passage times below a level. And I think I made a mistake here. Let me correct it. So it should be minus y. So y is a positive or non-negative quantity. So let me put the minus. So you have this walk, and of course immediately it starts going down. So it passes through some levels, but on most levels, actually, on almost every level, it will not have an excursion, or it will be excursion of size 0. But at some point, and this is precisely the value here is psi 1 over q, it will have the first excursion. The first excursion above past infimum is born, and then it completes it, and then after that, it goes down to the second excursion. I mean, there will be a second excursion on this level, and then it goes down again, and there will be a third excursion, and so on. I should maybe erase this. So should have done it in the annotate mode, but okay. So this, and then this, and then this. Okay. So this was the simpler model, reminding you about some not so recent history. And now this is a reminder of the David talk, but so this is recent history. With Vitaly, we started studying stochastic block model, and then we wrote a couple of papers, and David joined us on the excursion representation and scaling limits, which is about to be written. It's work in progress, but we have advanced quite a bit. And so I decided to devote most of this talk trying to explain now the excursion, so encoding of the stochastic block model, more complicated version where vertices have mass. So it's more complicated than the model from David's talk, but it is in the same class of models. And in David's talk, I think he had a parameter called D. So it was the number of blocks or the number of types. But here I simplify. Of course, we study general setting, but for the talk, we have only three types. And it is good for me to give them colors. So there will be a block of green, a block of red, and a block of purple. Okay, and here it's written their types. And within each block, there are vertices, just like before in the Erdős-Rényi. You could think of Erdős-Rényi, not Erdős-Rényi, but the Poissonized, generalized, all this graph. So sitting in here, and sitting in here. But and they could evolve independently. That would be okay, but maybe not so interesting. For us, let me see, yes, okay, so I mentioned it already here. So inter-community interactions, that is what's happening inside, and then there is intra-community, what's happening between the communities. So we have some parameters. There is a matrix Q, because our M is free, it is just 3 by 3 matrix. Otherwise, it would have been M by M. And we have this is input data, the vector of weights. And okay, I decided just to have 4 vertices in the green, 3 in the red, and 3 in the purple. And you'll see it's already a bit complicated to write what's going on. But I tried. So let's see what happens. So here are these edges, which are inside of the community, and they arrive as multiplicative edges between, So for example, okay, here I have 3 parameters actually. This corresponds to the time of the coalescent in the M equals 1 case, in the Erdős-Rényi, Poissonized and generalized. This is this also, and this also. 3 parameters for the 3 communities. So for example, this edge here, it arrives, or the probability that it is here, it is 1 minus e to the minus qg times w1g times w2g. Okay, so you take the product of the masses and multiply by qg, and that's the rate. Or rather, that's the parameter. Okay. And similar for here, we have no edges at this point, but so the probability there is no edge here is just e to the minus qr w1r w2r. Okay, and here I drew some inter-community edges. I tried, this is between green and red, so it is green-red. This is green-purple. This is red-purple. So there are three such edges, for example. And again, the interactions are multiplicative. So did I write it here? Yes. Okay. Let's pass on to the next thing. Okay, then I don't have to write so much. So this is what I just wrote here, but it's small letters. And for this one, I'll zoom in. So the edge has again multiplicative exponential probability, multiplicative in the masses. This is for the green vertex, for the red vertex. But there is a different parameter, and that makes it harder. If all these parameters, all the q's were the same, qrg is the same as qpg is the same as qrqg, and so on. If all of them were the same, then it would have been one big community. Okay, so that is important to know. So instead of having one community, we split it into several communities because these parameters will be different. I mean, we want to study a model where they're different, and in the scaling limit, they will be quite different. I mean, some will be comparable, and others will be much smaller than the first group. Okay, but scaling limit, we are still not there. We are just preparing the ground. Okay, so I think I said, sorry for switching slides so fast. Yes, here I wrote, okay, it is just like 3 these Poissonized random graphs, and then multiplicative interactions due to these inter-community edges. Okay, so now, this is the slide that says the first steps of the encoding. It is just, I'm asking the question, is there an analog of Z, which was the simultaneous breadth-first walk, which encoded the graph, as we saw several times before, and I reminded you today. And is there an analog of these times infimum times, these are the, the times of passage when Z goes below some level. Z goes below for the first time. Okay, so again, we have some data. We have a matrix Q, which on the diagonal has QG, QR, and QP. These are the inter-community rates, and it is symmetric. On the off diagonal has precisely the rates. Okay, so maybe I can write it. Maybe I can write it here. So Q is Q. No, I want this. Q is QG, QR, QP, and then here it's QGR, QGP, QPR, and then it's symmetric. Okay, so this is copied. And we would like to do very similar thing. We would like to, maybe I can erase it actually. The other things won't get erased, yes. So instead of a single timeline, a single time for the process Z, which we had before, we have to be more imaginative and have 3 timelines, one for each type, and from afar, on each timeline there will be something of this kind. Okay, so I'm zooming in, and we will see. So this is a bird's eye perspective. There will be a process. There will be something evolving at the unit negative drift, having exponential jumps, and size and the rate of this jump. Size of the jump will be proportional. Okay, this is proportionality symbol. Size will be proportional to the rate. This is what we had before, and indeed, I wrote down now these processes. If we had 3 independent communities running in parallel, this would be the corresponding breadth first walk for the first community. 4 particles, these are its masses, these are the size exponentials, and this is its S, the green S. This is the same, precisely the same for the red, except we have 3 types with their masses, and the same for P, for the purple. Okay. So, and this is what is written here, that the size have these rates. That's, we've learned this. But in our more complicated setting with 3 timelines, it is beneficial to think more broadly and to introduce a kind of a skewing parameter, which is a vector non-null vector. Okay, so it might have one coordinate 0 or more coordinate 0, but it cannot be all 0. And in some of our most important applications, it will have all positive coordinates. Okay, so so here is an example. So I put rho equals 0, 1, 0. For that, I need to go to page 7. So we, in fact, okay, let's read this, and then I'll go to page 7. We give, or we may give preference. Okay, so this is wrong. We may give preference to some timeline or some communities over the others. So we explore more certain types. And this will influence the law of the order in which we will, in which the connected components are discovered. It will influence the order, but it is not part of the model. So if you recall, the model had just Q and W. And if rho is, for example, of this kind, if it has 0 on some of the components, let's see. So let's go to page 7. maybe it is this one. So now I don't know which one it is. Might be this one. Let's take this one. Okay, so we had 0, 0, 1, 0, meaning that we will discover the red. Okay. There is a question.
No, let's continue.
I'm sorry.
Let's continue.
Okay. You will see very soon. So rho is positive only for one of the colors, one of the communities. This means that we will start from a vertex in this component. It might be this one, and then it is the whole component. And then we might discover, then next component that we will discover will again start from the red vertex. And it might be either this one or this one, the remaining ones. If it's this one, then we will discover this. And finally, we will go to this and discover this component. But, okay, I think this is the page 7. We will never discover this one, okay? The components which do not have this one, does not have red vertices, it will not be discovered by our algorithm. For that reason, okay, so this is just a side note. It will not be encoded, but if we allow ourselves to have at least a little bit, an epsilon on each of the coordinates of rho, then we will discover everything. Okay, so now we go to the actual encode. So here's the influence of rho. We have this parameter rho on the first vertex. So, and okay, I told you a little bit about it. What we do, we have a single parameter y. Okay, this parameter y, it's auxiliary parameter. It is just the y that was before running in T of y in the m equals 1 case. So here again, so y will be on all timelines. It will be on each and every. So there are 3. We have the same y, but actually it is multiplied by rho. Okay, here it's multiplied by rho g, by rho r, and rho p. Let's suppose that they are positive. In this picture, they are. And here, in fact, I even said that rho g is 1, rho r is 5, and rho p is 1. So the red has a preference, but it is not infinitely many more preferred. It is just 5 times more preferred. And the meaning of this is y is running, when y is running from 0 to infinity, we are actually scanning. I don't know if you can read, this says scanning through the infima of ZG. So this is the beginning of the graph of ZG. This is the simultaneous breadth-first walk for the green line. So we scan through the infimum at the speed rho equals 1. And we go like this, okay? And at y, we are here. But now for the red line, we scan through the infimum at speed 5. And when for the same y, we are already here. So we scanned all this to get to the infimum, okay? And here we just scanned this much. And for this line, we also scanned this much. So we got all the, okay, this is a, I again drew the problem with the cable, no?
Oh, yes.
Let me try. Okay, maybe it will reconnect. Yes, it reconnected. Okay, sorry about that. I drew the masses. So these are the individual masses of the green, the red, and the purple, and also the jumps. The jumps will be equal to the mass. Okay. we insist on scanning through at different speeds. And since 5 is here, it is the preferred direction, even though this jump on the red line, the jump is a little bit further than this one and this one, actually the speed at which we go, we will discover it first. And this will be the initial, it will correspond to the initial vertex of the encoding. And so the first vertex discovered is the red 2. It is why is it 2? Because this is psi 2r. Okay, I didn't write any longer this pi is the size bias permutation. I wrote just the individual, individual indices. Okay, so now this was easy in comparison to what's coming. So this is maybe the hardest thing to take from this talk, and I hope I explain it reasonably well. So what's happening now? We have the first vertex, and this is this green. Okay, let me reinforce. The green bit was when we scanned for the first jump. So here we scanned much faster, here we scanned slower, and here slower. Okay, and we got to the first jump. And of course, on the red line, it is the jump on the red line. We do the usual step. That's the okay, maybe without the tail. So the process just jumps by the amount W2R, and this is what's written here, W2R. However, on the other timelines, we don't have this jump yet. There will be a phantom appear. So think about it. We have to listen for the neighbors. So these are these red regions. We are going to listen here for the eventually for the type for the red vertices, which are linked to the second to red 2, but also we want to listen for the intra-community edges. And so on the green line, we are listening for amount of time, and also on the purple line, we are listening here for an amount of time. And now I had to come up with some parameters. Oh, sorry about that. I'm trying to, okay, I'm trying to just, let me, for some reason, maybe I take this, I go to some other mode. Yes, okay, maybe in this mode it doesn't allow me to. Okay, sorry about that. Okay. And then this, okay. So how is this decided? These are these yellow things. So I have, let me write it, maybe not, I'll go to annotate. So, okay, with tail. So this is QRG divided by QG. It is a parameter, and here I put it to be 1, and therefore this interval has the same length. This one has W2R, and this one also has W2R. But here, this is QRP divided by QP, and it happens to be 0.3. Therefore, the length of this one is a third of W2R. I multiplied. This is what's written here, 0.3 times W2. And also, I drew some jumps. I drew some jumps here. It is the jump, a phantom jump. It's not part of this process, but I draw it on this timeline anyhow, and it has the same length as okay, same length as the as the listening interval, and the same thing here. This jump here has the length of the listening in. And the next slide explains it. Okay, so maybe this is the gist of this talk. Zoomed view of lines G and P. Exactly. Okay, I'm glad that I did this before, that I don't have to write it now. Okay, so this is the zoomed view. We have this on the red line. I did not write the red line because it's clear. We had the red jump. It jumped just as if we had one type. But on the green line, we have this phantom jump, and we have the phantom listening time. And here we are listening for the green. So it is important to note that the listening here, it is for the green. And here, the listening is for the purple, here. So on each timeline serves us to listen for the vertices of that type. However, we pretend, okay, so we pretend to have this jump. Later on, I'll explain how to, rigorously put it in. So here, what does this say here? So here is the green, psi j green divided by qg. So these are as before in the m equals 1 setting when we just had one community. We want to see whether this belongs to this. Okay, there is some filtration of the past, and we know that this psi j did not arrive, the green one did not arrive in the past. Well, we want to have this probability. It is an exponential, just in like it has to be in our network, and this is the degree corrected stochastic block model probability of connection, and we need to have this in here, and therefore, and also we need to have the same for the purple one, not the same, but with the parameter QRP, because it is the interaction. We are here looking at, so we have the red 2. And then we are sending the message, we ask, is there a red vertex connected to it? Is there a green vertex connected to it? And is there a purple vertex connected to it? And on each of the lines, we check, and we check by these intervals. We check for exponential random variables, and we need to, that's how we decided to do it. Maybe there is another way, maybe there is a better way, but for us, it is pretty convenient to actually divide the size. Okay, here we don't divide by much because this is 1. But here we actually multiply by 0.3. Okay, so we divide by some number, or maybe we multiply by this ratio, for the reason that, okay, this is the first random variable that arrives on the red line. This is the minimum of all the, on the green line. And it will not appear during this listening period, but the probability that it doesn't appear. So let me write this. Okay. So probability that psi 2g over qg does not appear. So it's bigger than the red. Okay. Or no, let me just write it like this. Does not appear in the red. Okay, this bit. It is precisely, well, the escape. Okay, what is it? It is qg times the rate w2g, and then the length of this interval, and the length is qrg divided by qg w2r, and that's why I say 2 qg's cancel. And so you get this multiplicative. sorry. Oops. You get the multiplicative. Okay, Q's answer. And cancel, sorry. So these two cancel, and you get W2G times W2R times QRG. And the same, very same thing happens here. That's by same, it's analogous. Okay. So if you have questions at this point, I think, yeah. So, I mean, we can do other things later on. I have material prepared, but it would be good to ask now, you know, if I did not explain something well enough, I think that this is the right place.
Maybe let's go and see what happens. Yeah.
Okay. So we keep going. The process evolves. We discover more and more of the component. So, what happened here? What happened? Nothing much. On the red line. Otherwise, we would be done. So here on the red line, there was the red. There was red psi1 Q over Q red. That's the connection. The simple thing happened. It so this the vertex corresponding to this is connected to red 1. And this is what's happening here. So as before, there was the red 2, and now during the listening time, there is the red 1. Therefore, we keep exploring. And the next, a little bit darker red, it corresponds now to the red 1. And again, we do not only explore on the red line, we have to explore on each of the lines for the possible connections. So on the red, we explore for the connections between the red vertices. But on this line, we now will listen for whether this new darker red is connected maybe to a green vertex or maybe to a purple vertex. And it turns out that actually here, psi 2G over QG, it enters into the red interval, into the dark red, which means, okay, here we listen for the children of red 1, and we already see that it entered. And now we can, this is the conclusion. 2 is connected to 1, and 1 has one new neighbor, a single neighbor, 2 green, or rather green 2. And why is that? Because there is no other vertex, no psi. Other psi's happen later on this line. So here we have maybe other psi's. And here, when you check carefully, there is also no purple. The first purple is here, so it did not connect. Okay. So now I suffer a little bit, but okay. We successfully made zoom in and zoom out. And so we now know more about the graph. We discovered one component. We started from 2 red, went to 1 red, and then to 2 green. And now it's the time to listen for the first time. We switch from the red to green. We now listen to the children of a green vertex 2. On the green line, it's simple. We just use the size of the mass of the green 2 for the listening interval. But on the red and on the purple line, we do something else. Remember that we had to divide through, divide through as before. So here I write what is written here in yellow, QRG divided by QR. So this bottom thing belongs to the R, to the line where we listen, and here is QPG, the intra-community rate, QPG divided by QP. And it turns out that this is 0.5. Therefore, this green interval, its length is twice the size of this one. So here we half it and listen for the children, for the new vertices on the red. And here, this is a comic relief. I put a very small very small ratio, 1/100. And so I zoom in. So you see there is this green interval here, and it's still, the purple is not there. The purple did not make it. There is no purple connection, and there is no red connection, and there is no green connection. So this means now that we have discovered the first connected component, because we went through all of its vertices, 2 connected to 1, 1 is connected to 2, and 2 has no new neighbors. All that we went through, all the possibilities, and this is, the end of the first connected component. And so what did we actually do? This is a more rigorous, it is a rigorous statement, although not as formal as we wrote it up in the paper, and with a little bit different notation. I'm keeping, the sizes of the clusters. It's just for this example. So we have 3 communities, we call them green, red, and purple. We have number of vertices in them. Everything is finite and relatively small. And there are these rates, ratio of rates, which appear in the picture. Okay, so these are important. And so what is this? This is actually a random field. So the true and phantom jumps, these phantom jumps that were not truly happening on the line, we include them by varying the parameter. So, for example, this is the first component of this random field, and the same is for all the others. So here it is the green. This corresponds to the green vertices. Green vertices listening for the green vertices. This bit corresponds to the red vertices. Red vertices listening for the green vertices, and this corresponds to the purple vertices listening for the green vertices if they are friends, if they have edges between them. And similarly here, this is for the red vertices which are listening for the red, green vertices listening for the red, and purple vertices listening for the red. So something to take away from this talk, this corresponds actually to what I drew, so to the pictures on what's happening on the timelines, and on each timeline we use the timeline to listen for the children, because we are actually drawing a spanning tree and spanning forest, component by component. We are encoding a spanning forest of this graph, and the different timelines serve us to make or not make connections. But each timeline is for, in fact, you see this here on each time. So on green timeline, I have only psi Gs. These are the ticks. On the red timeline, I only have psi Rs. And on the purple, only psi Ps. So this is, important. And after we have that, we have also an analog of the T, of the one-dimensional time of, passage. So it's actually a process. Here it's a vector value. Before it was real value. It's a process of passing through the levels, negative levels. But here we go in the direction of rho. And so this X, the random field, is truly a true analog of Z. So the Z, the simultaneous breadth first walk, is the simplified version of this random field. Here we have 3 parameters in the m-dimensional setting or m-type setting. We would have m parameters, but and this is, more or less the same definition. We are looking for the infimum of all the s's, such that the field goes down. The first time the field goes, this is the left limit, just as in the one-dimensional setting, and goes below y, but actually goes in the direction rho below y. And okay, this slide is not so much about t. It is more, we will get to that. It is about these lengths. So we have something that I decided to call quasi-excursion. They look, here I drew all the jumps, the phantom ones and non-phantom ones. And also here, it is somehow, okay, it's not so precise, it's informal, but we can still do it, and because we know what we did. We listened for the children repeatedly. We listened it here and we listened it here. Okay, and what happened? Well, we can just record how much time we spent listening, and this is the amount of time we spent listening. Precisely this. Due to the fact that actually QRG divided by QR is 1. Okay. Exactly. No, I wrote it. Sorry, I'm a bit tired. It's written here. So it's QRG. It happened to be 1, but in general, it would be that plus QTG because there was a green vertex. Here on the red line, we listened to the W2R. That was the first vertex that ever arrived. W1R corresponding to the second vertex. And then we had to listen for the green, children of the green vertex, and that was already multiplied by this ratio. And on this timeline, we listened, we didn't have purple vertices, so we just listened with these ratios. We went through the children of red, there was none, and then the children of green, there was none. Okay, so that is what happened. And then I have a next slide, which is more, so now these are smaller, you don't need to read them, we went through that. But here we could look at the levels, okay? So remember, at the very beginning, I told you maybe, okay, we had 1, 5, 1. That was the row. And we were scanning, that was this. We were scanning through the levels, negative levels of x actually, but at the very beginning x is equal, for a while it is actually equal to z on each on the 3 components. It is actually zg, zr, zp. And then starting with the first jump ever, it changed. So the field changes, but it keeps for a while. And so what happened? So we followed through here at different rates until we go to the first jump that happened to be red, and we stop at some y, and that y is random. Okay, y is the parameter here. So t of y. Okay, it belongs to the t, and so this level is minus y times rho g. This level is minus y times rho r, and this is minus y rho p. Okay? And the claim here is that y is an exponential random variable, and we can compute its rate in real time. So let me switch to the, okay, maybe black. So it in fact is, and I'll just write it and see if you agree. It is rho g times W1g plus W2g plus W3g. How many green? I think there were 4. There were 4 green vertices plus rho r times W1r plus W2. I'm just going through all the vertices and I'm adding their weights and I'm multiplying by the rho. W3R and plus rho purple, W1 purple plus W2 purple plus W3 purple. It has to be that because of the way T is defined. You are actually, due to this skewing, okay, by rho, if rho were 1, 1, 1, say 1, 1, 1, then we would just be looking at the minimal exponential on this line and comparing it to the minimal exponential on this line and on this line. And it would be, just the sum. We would not have that. But because we have skewing, the fact that we do this, it corresponds to the multiplication. Somehow it is 5 times, because this is 5, say, 5 times more likely to encounter first, not 5 times more likely, but the rate is 5 times higher for encountering a red particle first from the rate of encountering the green or the purple. And this is what this says. And okay, so that's very nice that these y's are exponential, and it is part of a more general picture, nice picture, where here I draw. I'll talk about it soon. I think if you let me. I'm not sure how much time. Ooh, I went over time. Okay. So let me. I mean, would you like me to stop here? I could just say it's part of the more general picture.
You can have just maybe
Okay,
10
thank
minutes.
you. That's very generous. I'll finish, I promise, in 10 minutes. Yeah. So the encoding is analogous to the M1 setting. So this is our M3 setting, say, and we, what is this slide about? It is about the jumps of T. So this is what I call delta T, okay? T is in fact left continuous. It is easy. It is not the most natural, but in our setting, it is the most natural thing to have T to be left continuous. It's because it is an inverse of something. So it is a left continuous process with positive jumps, and I mean positive. Okay, so if it jumps, it is a vector value jumps, and all the components are positive. These are the lengths. Here we had quasi-excursions, right? This is what I call quasi-excursion, the 3 quasi-excursions, this you can ignore, rather here we have. And these are their lengths. And in fact, at this time y, which is exponential, we computed its rate, t made a jump. The vector value t made a jump, and the value of this jump is precisely the length of these listening period, total listening period, where we go over all the vertices that happened, that arrived, and their listening times. And what I say here, okay, most of the time T will not jump. It is a nice process. It has, it will make finitely many jumps in our setting. Most times it's continuous, almost everywhere, and that's when when it doesn't jump. That means that it is like this. There is this level here, and nothing happened. There is no no news from any exponential arrival of a vertex. And this happens also if and only if there is no connected component, because we are reminding you, we are discovering connected components of our stochastic block model by passing through these timelines, and we do not pass through them, just scanning them at the same rate. We have a bias, maybe bias in certain direction. I mean, in direction rho, or at least skewing, not biasing. Biasing is stochastic. Okay. And I think, okay, I've said everything that I wanted concerning this slide, but okay, so if I didn't say that, somebody would ask, what happens now? You've discovered only one excursion of your graph. So can this be done over and over again? And indeed, due to the exponentials are the nicest continuous random variables, in my opinion. So due to the Poissonization, of course, you can keep going. So the multi-time point, so you can view this as a time point. So what this is, it is the amount of time that we spent listening, but we didn't even see the first vertex. This is this time, plus everything that we spent listening here. Then for this, it is the amount of time we spent listening here, plus everything else that we did on this line. And this is the amount here, and everything else that we did here. So before, it is still before this purple jump. So this multi-time point becomes the new origin. I hope this, is sufficiently clear. So I even drew this orange thing, orange tick. So at this end, there is the orange tick, and here it still happens before this purple jump. But I think the next vertex that will be discovered is going to be purple, clearly, because here's this one, and this one is just following this new origin. So 2, 1, and okay, this is wrong. I didn't mean to write G. So the red 2, the red 1, these are the vertices that we've seen before. And of course, the 2G. This should have been the green 2. They are here. They are in the past. And because of the exponential quality of, Poisson type quality of our timelines, we can just keep going. We have the first excursion, but now the time in front of us is completely fresh, and we keep scanning again. Our T is defined so that we will scan the red line a little bit faster than the 5 times as fast as the green or purple, but we can keep going, and we will discover the new connected component, and we will make a new excursion of the quasi-excursion on each of the timelines, a triple of quasi-excursions. And okay, so this is, almost the end. I now wrote an uglier slide than anything that you have seen. Let me see if I can move. Yeah, I can move it like here. This is actually a slide with the notation. I mean, when you write a paper, you cannot, in fact, yeah, there are so many colors, there are so many letters, but numbers, there is infinite number of numbers. So we switch to the indexing. Instead of colors, we switch to the, let me use red. We switch to the finite number of types. And these are the, these correspond. So now the types are I and J. There is a matrix valued process where the ith J component is what you saw before, but now it has new look. Only when I equals to J, only when you're on the diagonal, there is this negative drift. These are the inheritance from the Erdős-Rényi setting, the inherited, and here this is 1 because QII over QII is 1, so you truly see this ZG, ZP, ZR. And then when you're not on the diagonal, you see these are the phantom jumps. And what do you do here? Well, you arrive, so the field, not the process, I always start pro and then I say the field. The field is actually summing through the corresponding parameters. So with the, J is the type, and then you have to sum through and sum. So this is x1, x1j, and then this should be x2j of sj, and this sum is xmj of sj, and then this is just the same definition defining T, but we have this matrix R. This is the matrix of quotients. And of course, my color is red, so that would be very confusing if I introduced it earlier. But now the types are integers. So I mean, not integers. Yes, they're integers. Yeah. So I have now a matrix R. I have a row. There is this graph. And okay, what does the theorem say? The theorem is truly theorem. Okay, now I'm moving this. Okay, never mind. Theorem 2.6 in our paper. The paper is on arXiv. It's a preprint. The theorem is written not like this, but it uses this notation. Okay, it uses this. And so we have a row which is non-zero. And it says that the above, okay. Well, maybe so this is actually wrong, what I wrote. Let me write, to correct it, to correct the statement, I should write row, not U, row I is bigger than 0 for every I. So may I, I'll change. There is also a statement about this more general statement, but then I would not have this all the connected components. And that would correspond to the comment we had early on when we had row equals 0, 1, 0. And there was part of the graph which did not have red vertices of the red type red, and it would not be discovered. Okay, so let's assume that actually row is nicer than this. And the above encoding, the encoding that I showed you, it can be done in this general setting, and it will eventually discover all the connected components. Each component can be matched uniquely to a jump of T. In fact, as you go through the jump of this passage through levels process, they will, every time T jumps, there is a new component, and the matching, and it can be matched. It is the jump of T is, again, you just listen to for the neighbors of the vertices that you have discovered, and there are M tuples of quasi before we have the triple. M tuple of quasi excursions, one for each timeline. So on each timeline, you have this quasi excursion. And moreover, the size of the jump, so this vector size, each component is something we can represent it in terms of this matrix R and a certain vector. And this vector has natural interpretation. You just put the mass of type 1, complete total mass. So by this, I mean all the vertices that are in this corresponding component, but they have type 1. All the vertices that are in the corresponding component have type 2. All the vertices that have type M. And this is, so if the jump happens at level Y, then this is for the excursion. No, this is the excursion that can be matched to that, the unique excursion. We could call it excursion encountered at level Y. And then I again remind you that almost everywhere, for almost all levels, there is no excursion. So the M will be 0, but there will be exceptional random Ys, which are exponential uh, conditional. They are exponential random variables, even independent exponential, but in some conditional way, which we explained in the paper. And for these exceptional times, just like in the figure here, for these Ys, where you have first, and then at some point later, here you will have second and second, okay? So there will be sequence of Ys, Y2 rho G, Y2 rho R, and so on, which have nice joint law. The point is they have nice joint law, and this says last but not least, M tuples of quasi-excursions arrive in size-biased order. Okay, so this is complete analogy, and it's very pretty that even in this much more complicated setting, we arrive to, we have a control on the order of arrival. Control. This is not control in the sense of controlling, but we know about its law. So we have knowledge about the law on the order, and that's important for us. And also we have the knowledge about the joint law of these exceptional times. That's the same theorem, let's say. And there are so many, the number of excursions is some finite number, and we have these exceptional timelines, exceptional times for the T process where good things happen according to what I told you above already. And I think this is the very last slide. Yes, this is, I didn't write the end, but I'm grateful that you listened to the full presentation, and that and sorry about the technical and technological problems, but I hope overall it was
Okay. Thank you very much for so colorful presentation. It was interesting to see how this multidimensional and multi-parameter random field arise. Maybe somebody have questions or comments, please. From the technical point of view, it reminds me the multi-parameter martingales. And I think that when you will study some scaling, you definitely will face such processes.
yes. I think it becomes very, very complicated. So what actually, I did not say much about that, and perhaps Vitali addressed this, because Vitali, I think you gave a talk in this seminar maybe a year ago. Maybe a year ago, it was kind of when we had early results. And there is a trick that we do. So we cannot, we do not know how to treat the multi-parameter scaling limits unless we assume an additional condition. There is an additional condition on this matrix R. Sorry. So that is a very good question. So, and I think another talk should be done, not necessarily by me, but in this series, there could be an interesting talk devoted to the fact. Let me just, I think maybe my pen. Okay. So there is this matrix R, and maybe I even write it. Just a sec. So R is, we could write it as Qij over Qi. Ij. So it is derived from matrix Q through these natural encoding. I think very natural encoding. Now, there is a way of making the projection, I would say, projection to processes, okay, under some condition. So you can pass from there is a condition on R saying that R has to be of the form Rij, has to be for some specific row, but row has this role of it helps us skewing the way we go through the vertices and the components. So if we have, maybe there is a parameter in front, but we have row I nu j. If Rij is of this form for all I different than j. Okay, let me just move this a little bit. So for all I different than j. So the off-diagonal terms have this form. Then we can, we found a way, and honestly, Vitali, it is Vitali's genius that found the way. We found a way of projecting so that we can now have a process, a stochastic process, which has excursions. So there is which has excursions which have the same same side. The size is this. Let me see. Okay, it is the I guess the size. No, the size of these excursions. Help me out. Is or rather, okay, let me not go into the details. It is a way of reparametrizing. So it's a way of making up a single curve. So there is a curve with a single parameter S going to gamma S. Okay, and then we can plug it inside of the process. Not the process, the field. Okay, we plug the curve inside of the field. Vector curve inside of the field. So maybe I should write on a new on some page elsewhere. So there is a under certain nice condition, we can construct a continuous curve with some very nice properties, such that, for example, the norm of gamma S is S, and also that T of gamma S, that's remarkable. T of gamma S is the norm of T. T of gamma S, so is, I guess, S.
No, Vlada, you need to define this topic pin time associated with the process, right? And then say that norm of T is exactly S. Probably.
Norm. Okay. Let me know. Yes, let me not go into that details. But do you agree, Vitali, that the norm of gamma S is S?
Yeah.
Continuous.
Yeah.
Continuous curve. We plug into instead of the dimensional data, we have one-dimensional data, but we plug in gamma into these are xi's in my field. So x is x1, x2, up to xm, and each of these x's depends on vector valued quantity. And gamma can be plugged in, and now we follow. We can express the jumps of t. I guess the jumps of t through the jumps of s, which is just following this stochastic process. It's the infimum of when xi gamma s minus goes below ri rho I y. So we get one-dimensional representation of our multi-dimensional problem, and that is only under this. I mean, for now, this is if and only if. And there is also probabilistic interpretation of what this means, but okay, this can be done.
Actually, it was my question. I was thinking about possibility just to take a sum of coordinates of your random field x and just discussing its behavior. And it occurs that after the change of the time, you can consider these coordinates like separate process. Yeah, you don't need information about other process. Am I right?
I did not quite follow when you would take the sum of xi.
No, not some. I want to make just take some of this x, some subset of coordinates.
Subsets of coordinates.
Yes. And then just look at it, and can it happen that we can consider the subset again like the process of such type? And it looks like this because after this changing of the time, you can consider separately just coordinates. Yeah.
Yes. I mean, in this construction, the components are related. So you're asking how much information is in each one.
Yeah. Just think that the information which is hidden in the, for example, component is reflected in the length of this red interval. That's all for other components. Yeah?
Yes.
Yeah,
I understand. Right. I mean, I don't claim that I or we. I mean, some of us may understand this more than others, but no one has explored. We have done something. No one has explored this in depth. I think we got some progress on this, and I think it's interesting. But I think there might be more structure, just like you suggest, more structure to explore. For now, we've explored this structure, and it's complicated. I mean, trust me, it's complicated enough, and this has to do with I don't know, Vitaly, in your talk, did you go through through this elementary but still technically somewhat demanding analog of composed with, so what we called continuously composed with. So we had to you know, we still had to invent some math, not really invent math, but we had to write pages of rather elementary kind of calculus textbook definitions, computations, comparisons, analysis. We had to write 10 pages, or okay, maybe on the order of 10, just to sort of say, okay, we haven't seen this type of construction before, because gamma has components gamma 1, gamma 2, gamma m, and each of these components is actually defined as this continuous composition of something with something. And let me not, there is GI with kappa, something like that, right? Or kappa inverse, I forget. But, I'm not telling you what the GI and what kappa is. So these are the inputs from our data. They are kind of derived from our timelines, But in fact, this is a completely deterministic. So we do deterministic analysis, and then we plug in our specific processes into the deterministic world. The results that we obtained for the deterministic functions of several variables. Now, okay, perhaps we've missed something. I mean, I'm not saying that we didn't, but somehow the projection that we do in this specific setting, I think it deserves some attention, but at least we wrote a paper. So what I told you today is the first half of our first paper, in some sense. It is one result, and then there is the second half of how to make this projection. So how to define this. There's some special situation where this is just the composition. These are natural maps, just the composition. But if you, in the most simpler of our cases, when you want to plug in the random, these Poissonized processes with true and phantom jumps, when you want to plug this in, you need to use the new operator. Okay, so we did this, and we arrived to the description in terms of infima of a now we can take one component of our random field, we plug in the gamma, and we have a process, and that's what saves the day for passing to the scaling limit. So in the article that we are writing now, we are using, we have to assume the same condition. This one we assume for the nth model. We have this, okay? And so all of our models are now such where the projection is possible, and therefore there is a scaling limit, and it's still new territory. I mean, new to us and hasn't been done before.
Okay.
So I'm not, yeah.
But
yeah, okay.
Vlada, maybe
Yes, go ahead.
But maybe one should say that these assumptions that we put rho I and nu j, it is not a technical assumption. Here is like a very nice structure that when you consider each block as a vertex, and you assume that vertex between this, like edge between these two blocks appears if and only if there is an edge between two of vertices, these small vertices inside the block. And if you do that, and if you see, again, multiplicative coalescence, then it is exactly this assumption which guarantees that. It is if and only if.
Right. So, yeah. So, so what Vitaly says, so also in this, okay, so I cheated. I maybe talked about a little bit, half minus epsilon of a paper. And there is another half plus epsilon, half minus epsilon, what I told you about this construction in this setting. And then there is this epsilon, interesting comments. So we have a section where we discuss this condition, and it's like not a page and a half. And it turns out that there is some hierarchical structure inside of the model under this condition. So it is a special, yes, okay. One, I wish I understood. You know, for now we have the correspondence between this condition and this structure, additional structure of the model, and we have correspondence of this condition and this kind of way of representing our T's inside of in terms of the stochastic process, but I don't think, at least in my mind, it is not yet clear how I would take this, go to this picture. I tried, but I didn't have time. Go to this picture and somehow see on the picture that I can do this. Okay, so maybe Vitaly can do that. If you cannot do it, then I'm not so much behind. But it would be interesting because you see what I mean. We have we already.
Vlada, sorry, but I think that
not a problem.
we have to stop. It is really very interesting. So we will wait for continuation.
Yes.
Okay, good. But now we have
by all
to stop.
means. Thank you very much for the invitation
and thank you for very interesting talk. Georgi, who will be the next speaker?
The next speaker is Alexander Weiss.
Oh, I see. Krylov very technical expansion for generationless interaction.
Yes.
Okay. Then thanks everybody and see you next week. Bye.
Thank you. Bye.
Bye.